An ancient mapmaker once charted a continent without ever leaving the ground. Long before satellites, these pioneers achieved astonishing precision with little more than ropes and stars. By the end of this, you will understand the forgotten sciences that mapped our world with stunning accuracy. How did they measure the entire Earth using only geometry and the sun? What monumental secret did they uncover that we still rely on today? How far can human ingenuity truly reach when faced with the impossible? Every spring, the Nile River would overflow its banks, swallowing the familiar lines of the farmland. When the waters receded, the landscape was transformed, a blank slate of rich, dark mud. The farmers needed to know where their fields began and ended, and for that, they called upon the rope stretchers. These were the Harpedonapti, the first known surveyors. Their tool was a long, knotted rope, and their genius was a simple, unshakable truth of geometry. They knew that a triangle with sides measuring 3, 4, and 5 units would always contain a perfect right angle. By stretching their rope into this specific triangle, they could recarve perfectly square corners and re-establish boundaries with remarkable consistency. This was the Pythagorean theorem in action, applied with practical brilliance centuries before the philosopher himself gave it a name. But this was more than just a chore of resetting property lines. For the Egyptians, the orderly division of the land was a sacred act, a reflection of the cosmic balance maintained by the gods. The rope stretchers were not just technicians, they were intermediaries between the chaotic floods and the divine order of Mot. Their work embedded a crucial principle into the very heart of mapping. Accuracy must be reproducible. Anyone, anywhere, with a properly knotted rope could achieve the same precise result. This was the humble, powerful beginning of a science that would one day measure continents, all starting with a length of rope and an understanding of the land itself. The orderly world of the rope stretchers was built upon the stable ground, but another civilization was looking to the heavens for an even grander scale of measurement. High atop a towering ziggurat, a Babylonian astronomer tracked the slow, predictable dance of the stars. Night after night, these early scientists filled clay tablets with precise observations, compiling what would become the world's first detailed star catalogues. They were not merely stargazers, they were cosmic accountants, meticulously logging the movements of planets and the positions of constellations. They understood that the sky was not a chaotic display, but a vast, orderly clockwork. Its cycles were so reliable that they could be used to create a fixed, universal grid against which the entire Earth could be measured. This celestial framework allowed them to determine true north and the other cardinal directions with a precision that a simple compass could never achieve on its own. Their greatest gift to the science of measurement, however, was a number we still use every day. They divided the circle into 360 degrees. Why that number? It likely stemmed from their sophisticated base 60 numerical system, but it also elegantly mirrored their observation of the Earth's journey around the Sun, taking approximately 360 days. This innovation gave mapmakers and navigators a universal language for angles and direction. With this celestial cartography, the sky itself became a cosmic map. A traveler crossing a featureless desert or a ship sailing the open ocean could now find their way by aligning their position with the unchanging stars. The Babylonians proved that to truly understand the dimensions of our world, one first had to master the map written in the night sky. This celestial knowledge would soon inspire a breathtakingly ambitious question, one that required looking at the sun itself in a whole new way. A scholar in a candlelit room turns a brass disc over in his hands. It is an astrolabe, a universe in miniature. its surface etched with a spiderweb of fine lines representing the paths of stars and the circle of the horizon. This was not merely an instrument, it was a sophisticated analog computer, centuries ahead of its time. By suspending it and sighting a specific star along its central rule, a user could perform complex calculations of time and celestial position. For a surveyor on a long journey, this was the key to a fundamental question: where on Earth am I? By measuring the angle of the pole star above the horizon, the astrolabe delivered a precise answer: your latitude. This single piece of data, locked in the position of a star, allowed for the accurate placement of coastlines, mountains, and cities on a growing map. The true genius of the astrolabe was its translation of a three-dimensional cosmos onto a flat, two-dimensional plane. It took the vast, domed sky and compressed it into a portable, rotating disk of brass. This was a revolutionary leap, a bridge between the abstract theories of astronomers and the practical needs of those measuring the Earth itself. It encapsulated generations of observational knowledge into a tool that could be held in one hand, empowering explorers and mapmakers to chart the world with a new, star-guided confidence. But knowing your north-south position was only half the puzzle. A greater challenge still lay in measuring the world itself, a task that would require looking directly into the sun. A Greek engineer squints through the sighting tube of a bronze instrument, his world reduced to a single, precise line. This is the Dioptera, and in his hands rests the power to bend geography to human will. He is not merely looking, he is aligning, ensuring that the aqueduct he plans will carry water for miles with a perfectly consistent, gentle slope. The Dioptera was the master of angles, a sophisticated tool that measured both horizontal and vertical alignments with a degree of finesse that would not be surpassed for over 1,000 years. Its calibrated discs, often paired with water levels to guarantee a true horizontal plane, transformed guesswork into calculated certainty. How could you possibly cut a tunnel through a solid mountain from both sides and have the two crews meet perfectly in the middle? The Dioptera made it possible. It guided the relentless straightness of Roman roads across continents and ensured that vast bridges found their footing on opposite shores. Every one of these monumental projects demanded, and in turn generated, exquisitely detailed territorial maps. These were not sketches for decoration, they were functional blueprints for empire, dense with practical information about elevation, distance, and the lay of the land. The true genius of the Dioptera lay in its elegant simplicity. It had no complex gears or electronics. Its power was derived from pure geometry and mechanical stability, a testament to the ancient understanding that the most reliable precision comes from mastering fundamental principles. The data it provided allowed cartographers to move beyond simply drawing coastlines. They could now depict the world in a way that showed how to conquer it. This engineering precision paved the way for an even more audacious thought, a question so profound it would require measuring the planet as a whole. The Groma was a study in elegant simplicity. A surveyor would plant his staff firmly into the virgin soil of a new province, the cross-shaped arms holding 4 weighted plumb lines perfectly still in the calm air. His world was reduced to these 4 vertical strings. By sighting across them, he could trace perfectly straight lines across any landscape, carving order from wilderness. This was the tool of the Roman Agrimensor, and with it he imposed a dream of geometric perfection upon the entire empire. His first act was always the same, the establishment of the Cardo and Decumanus. These 2 main streets, running north-south and east-west, formed the unwavering axis of a new town, the literal crossroads of Roman civilization. From this central cross, a perfect grid of lesser streets and square plots unfolded, a template repeated from the damp mists of Britain to the sun-baked plains of North Africa. This was not merely urban planning, it was a powerful act of administration. A governor in Rome could look at a map of any colony and instantly understand its layout, because every colony was a variation of the same geometric theme. It made the vast, diverse empire legible and therefore manageable. The work of these surveyors was meticulously recorded on formal maps known as forma. These were not artistic renderings but legal documents detailing every plot of land, its owner, its agricultural quality, and its topography. They formed one of history's first large-scale, systematic land registries, a bureaucratic marvel that brought clarity to ownership and tax collection across millions of acres. The true legacy of the Agrimensores was this demonstration that a single, standardized approach to measurement could forge order on a continental scale, turning conquered territories into a unified, mapped, and governed world. Far to the east, in the courts of ancient China, a different kind of map was taking shape. An imperial cartographer would unroll a long silk scroll, his brush poised to translate a flood of data into a coherent whole. This was not the work of a single traveler, but the culmination of a vast, state-sponsored enterprise. Emperors understood that to govern a sprawling realm effectively, they first had to see it, and for that, they established history's first large-scale, systematic land surveys. Teams of surveyors, equipped with sighting poles and measuring cords, would fan out across the provinces, using a form of triangulation to meticulously chart the empire's mountains, rivers, and roads. Their work was driven by a powerful fusion of technological invention and bureaucratic might. Consider the odometer cart. This ingenious device, a complex assembly of gears and figure drummers, would automatically drop a ball into a container after traveling a specific, standardized distance. It transformed the subjective experience of a journey into a hard, mechanical number, providing the reliable scale that made large maps consistently accurate. Then there was the magnetic compass. While initially a diviner's tool for aligning with cosmic forces, it was the Chinese who first harnessed its power for terrestrial navigation. In the hands of a surveyor, the compass provided a constant, reliable check against the drifting sun, ensuring that the directions on his draft matched the true alignment of the world. The resulting maps were marvels of both science and art. They presented coastlines and river systems with a precision that would not be rivaled in the West for centuries. Yet they were also beautiful objects, often painted on silk and framed with annotations about local customs and resources. This reflected a holistic worldview where geography was never just physical. It was a direct expression of imperial power and cosmic harmony. A well-ordered map was proof of a well-ordered empire, a perfect mirror of the heavens here on Earth. This tradition reveals a profound truth, that the most enduring maps are born not just from brilliant tools, but from the organized will of a society that values knowing its own dimensions. A different kind of map was taking shape in the quiet of a monastery, far from the bustling ports and imperial roads. Here, a monk dipped his quill not to chart a journey, but to illustrate a divine truth. His creation was the TO map, a stunningly simple diagram of the world. The inhabited Earth was a perfect circle, the O symbolizing the eternal and unbroken nature of God's creation. Inside, a great T divided the circle into 3 parts, representing the 3 known continents, Asia, Africa, and Europe. This was not a tool for navigation, it was a sermon in ink and parchment. At the very center of this symbolic world sat Jerusalem, the spiritual heart of creation, while the distant edges of the map were often filled with fantastical beasts and strange peoples, illustrating the unknown realms beyond the light of faith. These Mapi Mundi, or world maps, were encyclopedias of belief. They wove together biblical events, classical legends, and historical figures into a single, cohesive image. Their primary purpose was to show a Christian pilgrim their place in a cosmos ordered by Scripture, not to guide a sailor across the Mediterranean. The geography was theological. Every river and mountain was positioned to convey a lesson, not a measurable distance. This reveals a profound tension in the history of cartography. While practical sailors were using remarkably accurate Portolan charts to navigate by the stars and compass, the learned elite in their libraries often clung to this symbolic worldview for centuries. The map was not yet a neutral representation of physical reality. It was a canvas for a culture's deepest beliefs and fears. It asked not where you were, but why you were there, and what your journey meant in the grand narrative of salvation. This symbolic tradition forces us to remember that every map, no matter how scientific, is ultimately a story we tell ourselves about the world, a story shaped as much by what we value as by what we can see. A Mediterranean sailor unrolls his chart, and the world he sees is not one of divine symbols but of stark, practical lines. This is a Portolan chart, and it is covered in a dense spiderweb of routes all radiating from intricate compass roses. These were not maps for contemplation in a library. They were working documents stained with salt spray and built from the hard-won knowledge of countless voyages. Their stunning accuracy, especially of coastlines from the Black Sea to the English Channel, did not come from theory, but from the compiled logs and direct compass bearings of the mariners who sailed them. Every headland, every bay was drawn from experience, a collective memory of the sea etched onto parchment. The true genius of these charts was the web of room lines. To plot a course, a navigator would simply align a ruler between 2 points on this web and read the constant compass bearing needed to sail straight there. This was a revolutionary leap, allowing for confident open water navigation instead of tedious coast hugging. The Portolan chart marks a profound shift in human thought. It turned its back on the symbolic world of the TO map, declaring that the true representation of the world would be written not by monks but by sailors. It was a map born from the magnetic needle and the logbook, a tool for those who faced the unknown with measured data as their only guide. This empirical approach, this trust in observed reality over inherited dogma, would soon inspire an even greater geographical leap, one that demanded a tool to measure the very heavens from the deck of a rolling ship. A silver disk, larger than a man, gleamed under the torches of the Sicilian court. This was the Tabula Rogeriana, the world map of Roger, a masterpiece forged not in isolation but through the deliberate fusion of all known geography. Its creator, the Muslim scholar Al-Idrisi, stood before King Roger II, presenting a vision of the world that no single traveler could ever have witnessed. For 15 years, Al-Idrisi had directed a project of staggering ambition. He sent his own agents on journeys and, more importantly, interviewed a constant stream of merchants, diplomats, and sailors who passed through Sicily's vibrant ports. He gathered every available account, from the Greek texts preserved in Arab libraries to the sagas of Viking explorers who had sailed the northern seas. His court became a clearinghouse for global knowledge, a place where Christian, Islamic, and Norse perspectives were weighed against one another. Al-Idrisi's genius was not just in collection, but in critical synthesis. When two travelers gave conflicting reports about a distant river or mountain range, he did not simply choose one. He analyzed their stories, considering the reliability of the source and the consistency of the details, striving to piece together the most probable truth. The result was more than a map. It was an entire geographical encyclopedia titled The Recreation for Him Who Wishes to Travel Through the Countries. This book provided a written companion to the Silver Planisphere, filled with vivid descriptions of cities, trade goods, and cultural practices from across the known world. It was a practical guide for a ruler who sought to understand the vast, interconnected realm beyond his own borders. The Tabula Rogeriana itself was revolutionary because it turned south to the top. This was a deliberate choice, aligning with the Islamic cartographic tradition that oriented maps towards the Qibla, the direction of prayer. For centuries, European scholars who later studied copies of this work were seeing the world through a truly global lens, one that challenged their own parochial viewpoints. This monumental collaboration between a Norman king and a Muslim scholar stands as a timeless lesson. It proved that the greatest leaps in understanding occur at the crossroads of cultures, where diverse streams of knowledge converge into a single, deeper river of truth. This fusion of global perspectives would soon be tested by a new age of exploration, demanding instruments that could guide ships across an ocean with no end in sight. A ship's navigator stands on the deck at noon, raising his quadrant to the sun. With practiced ease, he calculates his latitude, his position north or south. But as he lowers his instrument, he stares out at the endless, empty horizon. He has no idea where he is east or west. This was the Longitude Problem, a terrifying void in the center of every map, and it remained the single greatest scientific challenge of the age for hundreds of years. The consequences of this ignorance were measured in sunken ships and lost lives. A miscalculation of just a few degrees could mean a vessel missed its landfall entirely, running out of supplies in the open ocean or, worse, being driven onto a hidden reef. For the mapmakers on shore, this created a persistent, ghostly error. Coastlines on their charts would appear to stretch or compress over time, their true east-west positions shifting like mirages with every flawed voyage report. The core of the problem was time. To know your longitude, you must know the time difference between your current location and a fixed starting point, like the Greenwich meridian. Every 4 minutes of time difference equals 1 degree of longitude. But how could you possibly keep accurate time on a rolling, pitching ship in salt-laden air that rusted delicate mechanisms and through months of temperature changes that warped its parts? A clock that lost or gained just a few seconds a day would put you dozens of miles off course by the end of a long journey. The economic and military stakes were so immense that governments took unprecedented action. The British Parliament passed the famous Longitude Act of 1714, offering a prize equivalent to millions in today's currency for a practical solution. This ignited a fierce, decades-long competition between the finest scientific minds of Europe, pitting astronomers who championed a celestial method against clockmakers who believed a mechanical timekeeper was the only answer. This long, frustrating struggle underscores a profound truth that had eluded the greatest ancient surveyors. They had mastered the geometry of space, but the final, crucial key to a truly complete world map was the mastery of time itself. A navigator braces against the ship's roll, his world reduced to a sliver of brass and the distant line of the sea. In his hands, a quadrant holds the key to his north-south position. This simple quarter circle, marked with degrees and dangling a weighted plumb line, worked on an elegant principle. By sighting the pole star along the top edge, the hanging bob would point directly to his latitude on the scale below. It was an immediate, mechanical answer drawn from the geometry of the sky itself, yet its simplicity was also its weakness. On a pitching deck, the plumb line would swing wildly, and a single misjudgment of the horizon on a hazy day could send a ship many miles off course. This limitation spurred the invention of the cross staff, a clever tool that traded a swinging weight for a sliding piece of wood. The navigator would place one end of the main staff against his cheekbone, then slide the crosspiece until its top edge met the sun and its bottom edge kissed the horizon. The angle was then read from a scale on the staff. It was an uncomfortable, even dangerous practice, requiring a man to stare directly at the blazing sun, but it unlocked a crucial capability, determining latitude at noon. Now, a ship's position could be fixed under the bright midday sky, not just in the stillness of night. Despite their susceptibility to human error and the sea's constant motion, these instruments became the relentless engines of geographic discovery. Every reading, carefully recorded in a ship's log, was a single data point in a vast collective project. When cartographers back in Europe compared thousands of these entries from different voyages, they could begin to see patterns and correct mistakes. A coastline that appeared too long on one map would be trimmed back. A non-existent island would slowly fade from the charts. The process was achingly slow, a testament to the power of patient, repeated measurement. It was through this accumulation of countless small observations, each one a struggle against the elements, that the ghostly outlines of the world gradually solidified into the maps we would recognize today. The rolling hills of 17th century France became a vast geometric diagram, marked by a chain of giant triangles stretching from horizon to horizon. Under the direction of Jean Picard, teams of surveyors erected tall wooden signals on church steeples and distant hilltops. Their work focused on a single, monumental task, measuring the arc of the meridian with unprecedented precision. Their method was triangulation, the elegant geometric backbone of all modern mapping. It began with the careful measurement of a single, precisely known distance, the baseline. From each end of this baseline, they would use a new, revolutionary instrument called the theodolite to measure the angles to a distant, visible point, like a church spire miles away. With these two angles and the length of the baseline, they could calculate the exact distance to that spire without ever walking to it. That newly calculated distance then became the next side of a new triangle, allowing the network to leapfrog across the landscape, conquering mountains and valleys with pure mathematics. This process was brilliantly self-correcting, minimizing the accumulation of error that had plagued simpler methods of chaining distances step by step. The power of this approach was proven on a national scale with projects like the Ordnance Survey of Great Britain. Teams of surveyors covered the entire island with a dense web of triangles, producing maps of such staggering detail and accuracy that they became the definitive representation of the nation for generations. The contours of the land, the winding paths of streams, the precise boundaries of estates, all were captured with a clarity that had once seemed impossible. This was more than just cartography, it was a demonstration of a profound intellectual principle. By breaking down the immense, complex problem of measuring a continent into a network of small, solvable triangles, these pioneers revealed that the precise shape and size of the Earth itself was not a mystery, but a puzzle waiting to be solved. The entire planet could be understood one triangle at a time. The theodolite weighed over 1,000 pounds, a monstrous brass instrument that required teams of men to haul it up sheer mountain slopes. This was the daily reality of the Great Trigonometrical Survey of India, a colossal undertaking that consumed most of the 19th century. Under the initial leadership of William Lambton and later George Everest, the survey was an epic feat of both mathematics and human endurance. Its official purpose was to create a precise grid of the entire subcontinent, a map for administering a vast territory and moving troops with certainty. But its deeper mission was to measure the Earth itself, using the Indian landscape as a giant natural laboratory. The method was triangulation on a continental scale. Surveyors would establish a precisely measured baseline, often miles long on flat ground. From each end, they would use their massive theodolites to sight on a distant signal. perhaps a flag atop a hill many miles away. By meticulously measuring the angles, they could calculate the exact distance to that hill without ever crossing the treacherous terrain in between. That new distance then formed the side of the next triangle, allowing the network to leapfrog across the entire country, from the southern tip of India all the way to the foothills of the mighty Himalayas. The challenges they faced were immense. Teams battled tropical illnesses in the sweltering lowlands and endured freezing temperatures at high altitudes. They navigated dense jungles and crossed raging rivers, all while ensuring their delicate instruments remained perfectly calibrated. Political tensions in various regions added another layer of complexity to their decades-long mission. Yet through sheer determination, they pushed the great arc of triangles northward. When the survey finally reached the Himalayas, the true scientific prize came into view. By sighting their theodolites on the distant, snowy peaks from multiple known positions, they could apply the same trigonometric principles not just across the land, but upward into the sky. They were now measuring the giants of the Earth. It was through this process that a peak known simply as Peak 15 was calculated to be the highest point on the planet, a discovery later named Mount Everest in honor of the survey's relentless leader. The survey provided the most accurate data yet for calculating the exact curvature of our planet, refining our understanding of its oblate spheroid shape. This monumental project stands as a timeless testament to what human ingenuity can achieve with little more than geometry, mechanical tools, and an unyielding will to map the unknown. While the great surveyors battled with theodolites on land, a quiet, solitary struggle was taking place in a small English workshop. John Harrison, a carpenter and self-taught clockmaker, was consumed by a single, monumental challenge, building a clock that could conquer the sea. The violent motion of a ship, the corrosive salt air, the dramatic shifts in temperature, all conspired to render the finest land-based timepieces useless on a long voyage. Harrison understood that the longitude puzzle was at its heart a problem of time. If a sailor could know the exact time back home while also measuring the local solar time, the difference between the two would directly reveal his position east or west. He dedicated decades of his life to this pursuit, pouring his genius into a series of revolutionary machines he called H1 through H4. These were not merely clocks, they were mechanical ecosystems of counterbalanced weights and ingenious anti-friction devices, all designed to neutralize the chaotic environment of a ship. His first marine timekeeper, H1, used a pair of swinging balances connected by springs to cancel out the vessel's roll. His later models grew smaller and more refined, incorporating a bi-metallic strip to automatically compensate for temperature changes that would expand or contract the clock's vital components. The culmination of his life's work, the H4, resembled a large, precision pocket watch, a masterpiece of miniaturization that maintained its rhythm over weeks and months at sea. When a ship's navigator finally held such a chronometer, his power was transformed. At noon each day, he would note the local time by the sun's highest point. He would then compare this to the unerring time shown by the chronometer, set to the Greenwich meridian. Every hour of difference meant 15 degrees of longitude. The calculation was now simple, and the terrifying void at the center of the map began to fill with certainty. The successful deployment of Harrison's design in the late 18th century effectively solved the centuries-old longitude problem. It was the final, crucial link in a chain of discovery that stretched back to the rope stretchers of Egypt. With both latitude and longitude now firmly within their grasp, mapmakers could anchor the entire world to a precise, universal grid. Coastlines that had drifted like ghosts on parchment for generations were now fixed in their true, permanent positions, and the great age of global navigation was truly born. A brass telescope now sat at the heart of the surveyor's most vital instrument. This was the theodolite, transformed from a simple alignment tool into a masterpiece of mechanical precision. By uniting a powerful sighting scope with two perfectly flat, finely graduated circles, one for horizontal angles and one for vertical, it gave its user the power to capture the world in 3 dimensions with a single glance. The surveyor would center the instrument over a precise point, level it with meticulous care, and then peer through the telescope. By aligning the crosshairs on a distant signal, he could read the exact angle to that point from 2 different circles, locking its position in space within a web of unshakable geometry. This leap in accuracy was driven by subtle yet brilliant innovations. The vernier scale, a small, movable auxiliary scale placed alongside the main one, allowed the user to read fractions of a degree with astonishing ease, turning a rough estimate into a precise measurement. For the most demanding work, surveyors used repeating theodolites. These ingenious devices allowed an angle to be measured multiple times and accumulated on the instrument's circle, effectively averaging out tiny errors with each repetition. Through this process, they could achieve a precision of just a few arc-seconds, a measurement so fine it is equivalent to the width of a coin seen from over a mile away. Armed with this new level of fidelity, the great national mapping projects of the 18th and 19th centuries could begin in earnest. The theodolite became the engine of these monumental surveys, its telescopic sight tracing an invisible web of triangles across entire countries. Each measured angle was a single data point in a vast continent-spanning calculation. This network of precise angles and distances was then painstakingly translated onto paper, giving rise to the first true topographical maps. These were not just charts of political boundaries, but rich, detailed portraits of the land itself, showing the gentle roll of hills, the steepness of valleys, and the winding paths of the smallest streams. This instrument represents the absolute pinnacle of mechanical angle measurement. It was a faithful scribe, a device that could take the complex, living reality of a landscape and translate it, point by meticulous point, into the clean, immutable language of angles and lines on a map sheet. It was the final, crucial link between the physical world and its paper twin, a tool that made the entire Earth measurable, one precise observation at a time. The new republic demanded a new world, measured not by the arbitrary foot of a king, but by the Earth itself. 2 astronomers, Pierre Méchain and Jean-Baptiste Delambre, were tasked with a mission that would stretch the very limits of human endurance. Their objective was to measure a precise arc of the meridian, from the northern French port of Dunkirk all the way to Barcelona in Spain. From this single, exquisite measurement, they would define a universal unit, the meter, as 1/10,000,000th of the distance from the pole to the equator. It was a breathtaking ambition to anchor human measurement to the permanent dimensions of the planet. Their tool was the same triangulation that had mapped nations, but the scale and stakes were now monumental. They spent years erecting signals on church steeples and lonely hilltops, their giant theodolites sighting across the countryside to weave a chain of perfect triangles hundreds of miles long. Yet their scientific precision collided with a world in chaos. The very revolution that had commissioned their work also spawned suspicion and local violence. Delambre was repeatedly arrested by local officials who saw his strange instruments as tools of espionage. Méchain, working in Spain, suffered a terrible accident and later became psychologically trapped by a small, nagging inconsistency in his data, a personal demon that haunted him for the rest of his life. They battled illness, political turmoil, and the sheer physical hardship of their journey, all in the service of an unshakable Enlightenment ideal. The meter was to be for everyone, a democratic standard derived from nature, free from the whims of any ruler. When their heroic labor was finally complete, the metric system was born. This was the ultimate expression of a mapped world, a system where every measurement, from the width of a fabric bolt to the distance between cities, could be traced back to the fundamental geometry of the Earth. It showed that the quest to chart our world is inseparable from the need to define its very building blocks, creating a universal language of dimension that now structures our modern reality. The quiet certainty of geometry gave way to a more dynamic kind of mathematics, one that could bend and curve to fit the true shape of the world. Surveyors had long relied on the straight lines and perfect circles of Euclidean geometry, but the Earth is not a flat plane, it is a sphere. To represent its curved surface on a flat sheet of parchment or paper required a new way of thinking, a mathematical revolution that could translate a globe into a usable map. This challenge led directly to the study of conic sections, the elegant curves you get by slicing through a cone. A mathematician would visualize a globe wrapped within a cone of light, projecting its lines of latitude and longitude onto the flat surface in a predictable, mathematical way. This was the genius behind map projections like the one developed by Gerardus Mercator. His famous projection transformed the planet's spherical grid into a rectangle of perfectly straight lines, a miraculous distortion that made nautical navigation possible by preserving compass bearings, even as it stretched the polar regions into vast, unrecognizable shapes. Each projection was a different mathematical compromise, a choice between preserving accurate shapes, areas, or distances. The mapmaker was no longer just a drafter, but a mathematician choosing which properties of the real world were most essential to sacrifice and which to save. This deep interplay between abstract math and practical need did not stop with geometry. As the great triangulation network stretched across continents, a new problem emerged, the problem of error. In a web of thousands of interconnected triangles, a tiny, unavoidable mistake in measuring a single angle would ripple through the entire network, throwing the final calculation into doubt. How could you possibly find the most probable true values from a mountain of imperfect data? The answer came from a powerful statistical method called least squares, developed independently by mathematical giants like Carl Friedrich Gauss and Adrien Marie Legendre. Imagine you have a dozen slightly different measurements for the height of a single mountain peak. The method of least squares provides a systematic way to find the one value that minimizes the total of all the squared differences from your various observations. It is a mathematical balancer, a tool for finding harmony in a chaotic symphony of data. For the surveyor wrestling with a continent-spanning network of triangles, this was nothing short of revolutionary. It transformed surveying from a skilled craft into a rigorous predictive science. Every measurement could now be analyzed, weighted, and corrected within a framework of probability. The story of mapping is, in a very real sense, the story of mathematics itself evolving to meet the demands of measurement. Each new challenge on the ground spurred a new discovery on the page, and each new equation, in turn, gave mapmakers the power to see our world with ever greater clarity. A naval officer stands steady on the heaving deck of a clipper ship, his world reduced to a sliver of brass and glass. He raises the sextant to his eye, its mirrors dancing with the reflected image of the noonday sun. With a delicate turn of a thumb screw, he brings the fiery orb down until it seems to kiss the razor-straight line of the sea. This was the noon sight, a daily ritual of precision that locked the ship into its place on the vast grid of the ocean. The true genius of the sextant lay in its mirrors. Unlike earlier instruments where the user had to simultaneously look at a star and the unstable horizon, the sextant used a double reflection system to superimpose the image of the celestial body directly onto the horizon line. This optical trick cancelled out the ship's own motion, creating a stable, virtual platform from which to measure angles with astonishing accuracy. It transformed a wildly pitching deck into a stable observatory. This leap in precision created a cascade of reliable data. Every noon sight, every star fix, was meticulously recorded in logbooks that eventually found their way to hydrographic offices back in London and Lisbon. There, cartographers compared thousands of these independent positions, slowly correcting the charts. A hidden reef noted by one captain would be confirmed by the safe passage of a dozen others, and the collective knowledge of the global maritime community was woven into maps of unprecedented reliability. With a skilled navigator, a sextant could determine a ship's position to within a few nautical miles. This was the margin that made all the difference. It turned the terrifying expanse of an ocean into a predictable highway, shrinking the world not by making it smaller, but by making it known. The age of sail could now give way to the age of steam and scheduled passage, all guided by the steady hand of a man with a mirrored instrument, bringing the heavens down to the horizon. A perfect map of our spherical world is a mathematical impossibility. To flatten the globe onto a sheet of paper is to force a compromise, a necessary distortion that every cartographer must carefully choose. This fundamental dilemma gave rise to the brilliant science of map projections, where complex geometry transforms the curved surface of the Earth into a usable two-dimensional plane. Each projection is a different lens, a unique mathematical formula that preserves some properties of reality at the expense of others. Consider the revolutionary world map published by Gerardus Mercator in 1569. His primary goal was to aid sailors, and he achieved this with stunning elegance. The Mercator projection preserves angles, meaning that a straight line drawn on his map corresponds to a constant compass bearing, a room line. A navigator could simply draw a line between two ports and follow that single heading across the ocean, a gift of unparalleled simplicity for the age of exploration. Yet this navigational miracle came at a steep cost. To maintain those true angles, the projection had to stretch the lands at higher latitudes dramatically. On a standard classroom map, Greenland appears larger than Africa, when in reality Africa's area is 14 times greater. The polar regions are stretched into unrecognizable giants, a necessary sacrifice for the sailor's straight line. Other mapmakers chose different priorities. The Bond projection, shaped like a graceful heart, sought to preserve the correct area of each territory, making it valuable for land administration and statistical representation. The Mulwade projection, an elongated oval, also prioritizes accurate area, presenting a more truthful vision of the relative size of continents, though it severely distorts their shapes, especially near the edges. There is no single right answer, only a series of deliberate choices. The map you use reveals its purpose. A map for a pilot values true direction. A map for a conservationist needs true area, and a map for a world atlas seeks a balanced, aesthetically pleasing compromise. This entire field is a powerful reminder that every map is a model, a simplified version of reality built for a specific task. It forces us to ask not which map is correct, but what truth we need it to tell. The lines on the page are not the world itself, but a conversation between the globe's perfect curves and our very human need to hold it all in our hands. A man with one arm stood on the rim of a chasm so vast it seemed to defy measurement. John Wesley Powell, a geologist and veteran, was about to lead the first documented expedition down the untamed Colorado River, a journey into the greatest blank space left on the American map. His team, like others under Ferdinand Hayden and Clarence King, was not composed solely of surveyors. They were a moving academy, a collection of geologists who read the history of the Earth in layered rock. biologists who catalogued unknown species of plants and animals, and topographers who translated sheer cliff faces into contour lines. These great surveys of the late 19th century were races against time and against each other, with each leader competing for congressional funding and a place in history. Their primary tool for mapping this immensity was the plane table, a drafting board mounted on a tripod. From a known survey point, a topographer would set up his table, align it precisely, and then sight through an alidade, a ruler with a telescopic sight, toward a distant butte or river bend. He would then draw a straight line along the ruler directly onto the map sheet mounted on the table. By moving to a second known point and repeating the process, the intersection of these sight lines would pinpoint the new feature with remarkable accuracy. It was a method of breathtaking simplicity and painstaking slowness, building the map one line at a time directly under the open sky. For elevation, they relied on barometers, carefully noting how the falling air pressure correlated with their climb into the thin atmosphere of the high Rockies. This multidisciplinary approach yielded more than just lines on paper. Powell's harrowing journey through the Grand Canyon gave the world the first coherent theory of its formation, revealing how a river could patiently carve through a rising plateau over millions of years. Hayden's survey, with its stunning photographs and paintings of the Yellowstone region, provided the visual proof needed to convince a skeptical Congress that this land of geysers and hot springs was a national treasure deserving of protection. Their maps were arguments, their data a call to action. The work of these explorers did not just fill empty spaces, it created new American icons and helped forge a revolutionary idea that some landscapes are too magnificent to be owned and must be held in trust for all people. This was the final, glorious chapter of exploration by foot and horseback, the moment when the last great unknowns of the continent yielded their secrets to the steady gaze of the surveyor and the unerring line of the alidade. The brass theodolite, for all its precision, still relied on a human chain of sight, but a new sound began to echo across remote valleys and mountain passes, a high-pitched warble that marked the end of an era. This was the signal of the Tellurometer, an instrument that replaced the surveyor's tape with an invisible beam of microwave energy. For the first time, a team could measure a distance of 20 miles in minutes through fog or darkness without a single person setting foot in the treacherous ground between them. The principle was a marvel of electronic ingenuity. One unit would transmit a microwave signal to a remote receiver. The instrument would then compare the phase of the outgoing wave with the phase of the returning wave, calculating the distance between the 2 points by how the waves had stretched and compressed along their journey. This process, known as electronic distance measurement, or EDM, eliminated the 2 greatest plagues of traditional surveying: the cumulative error of dragging a chain over uneven ground and the atmospheric distortion that could bend a line of sight. A measurement that once took a crew days of backbreaking labor, wrestling with chains and clearing sight lines, could now be completed with a few precise button presses. This was more than just a convenience, it was a complete transformation of scale. Vast, inaccessible landscapes, from the deserts of Africa to the frozen expanses of the Arctic, suddenly became measurable. A single geodetic baseline for a continental survey, the foundational measurement upon which all others depended, could now be established with astonishing accuracy across a wide river or a deep chasm. The Tellurometer did not just make old tasks faster, it made new tasks possible, shrinking the most formidable obstacles into mere data points. It represented the fundamental shift from the mechanical to the electronic age, where the physical chain was replaced by an ethereal wave. This leap set the stage for the next logical step. If we could measure the Earth with radio waves from a mountaintop, why not measure it with light from a satellite? A bronze disc no larger than a coin is set into the stone of a city bridge. It is a survey benchmark, one small node in a continent-spanning web of precise coordinates. This is the Geodetic Network, the permanent and invisible skeleton upon which every modern map is hung. Think of it as the ultimate reference system, a framework of thousands of permanently marked points whose exact latitude, longitude, and elevation have been painstakingly determined. Every new road, every property boundary, every construction project is ultimately tied back to these fixed control points, ensuring that a map of one county aligns perfectly with the map of the next. Without this shared foundation, our world of mapping would be a chaotic jumble of conflicting information, where borders would not meet and navigation systems would fail. The most visible symbols of this network are the familiar trig pillars, those concrete pillars often found on remote hilltops. For generations, these were the vital high points for the great triangulation surveys, the unchanging anchors that allowed the theodolites' gaze to leap from one summit to the next. Today, while satellites have taken over the primary role of measurement, these physical markers remain as a backup, a tangible link to the methods that built the system. This entire geodetic infrastructure is a direct legacy of the rope stretchers and their quest for reproducible accuracy. It is a project that has never truly ended, a continuous recalibration of our understanding of the Earth's shape and our place upon it. The signals from the GPS satellites in space are meaningless without this ground truth network to translate them into precise locations on the ground. Every time your phone pinpoints your location on a digital map, it is accessing a system whose roots are buried in the Nile's silt and etched into brass discs on forgotten bridges. We live our lives within this measured world, a grand and ongoing collaboration between the ancient need to draw a line in the sand and the modern power to define a point in space. A surveyor's logbook was not just a list of numbers, it was a chronicle of a daily struggle against an unpredictable world. Each carefully inked entry represented a victory over 1,000 tiny variables. The finest theodolite, perfectly calibrated in a quiet workshop, would behave differently on a windswept hilltop under the blazing sun. Its metal parts would expand minutely in the heat, subtly shifting its readings, while on a cold morning the same instrument would contract. The surveyor had to know his tool not as a perfect machine, but as a living partner in the work, understanding its personal quirks and the precise corrections needed for the day's temperature. Then there was the atmosphere itself, a shimmering, invisible lens that could deceive the keenest eye. On a hot day, the air near the ground would bend or refract the line of sight, making a distant signal appear to waver and lift slightly above its true position. A mirage on the desert of data. Compensating for this required more than a formula. It demanded a seasoned judgment born from years of comparing observation against reality. This was a science deeply rooted in the physical, where the warmth of a hand on a brass scale or the humidity of a coming storm were factors as real as any mathematical constant. The resulting maps, therefore, were more than a collection of coordinates. They were a fusion of instrument and intellect, filtered through the patience and perception of a skilled individual. They carried the imprint of human perseverance, a quality no digital sensor can replicate. This long, painstaking conversation between the mapmaker and the world is what ultimately gave these early charts their soul. It was a relentless pursuit of truth, measured one careful, considered observation at a time. The surveyor's patient logbook, filled with thousands of local measurements, was about to be joined by a single, all-seeing eye in the sky. With the launch of the Landsat satellite in 1972, the very definition of a map underwent a fundamental transformation. For the first time in human history, we could observe the entire planet not as a patchwork of individual surveys, but as a single, dynamic system. This was not merely an improvement in accuracy, it was a complete paradigm shift in perception. The satellite's view was synoptic, capturing vast swaths of the Earth in a single pass, and its repeated orbits provided a continuous, living record of change. Patterns emerged that were utterly invisible from the ground: the slow creep of desertification, the seasonal pulse of forests, the silent retreat of polar ice. This new perspective birthed entirely new fields of science, from global climate monitoring to the real-time assessment of natural disasters. A flood could be tracked as it unfolded, a volcanic eruption's ash plume mapped for aviation safety, and the health of entire agricultural regions assessed from the unique light signature of their crops. The shift was as profound as the moment when medieval sailors abandoned symbolic TO maps for the practical, data-driven Portolan charts. It moved mapping from a discipline of local certainty to one of global context. The ancient quest that began with the rope stretchers, the drive to measure and comprehend the whole Earth, had finally reached its logical, breathtaking conclusion. The ultimate comprehensive view was not achieved by covering more ground, but by ascending to a vantage point where the entire planet could be held in a single, digital gaze. That single, digital gaze from orbit represents the culmination of a quest that began in the silt of the Nile. From the rope stretchers establishing sacred boundaries to the satellites charting continental drift, this entire history is woven from a single, continuous thread of human ingenuity. For millennia, we have been driven by a fundamental need to answer the question, where are we? The astonishing precision achieved by ancient surveyors was never a product of magic or mystery. It was the hard-won result of careful observation, mathematical rigor, and relentless innovation in the face of impossible challenges. Their true legacy is not merely the maps they left behind, but the very invisible frameworks that structure our modern reality. The metric system that defines our world traces its origins to the measurement of the Earth's own meridian. The global positioning that guides our travels rests on a geodetic network whose principles were established with chains and theodolites. The very concept of property and land management is built upon the legal and technical foundations laid down by the Roman Agrimensores and their counterparts across the ancient world. So the next time you glance at the glowing map on your phone, watching a pulsing dot chart your course through a city, take a moment to remember the centuries of discovery it represents. Consider the Babylonian astronomer who first divided the circle, the sailor squinting through a sextant on a storm-tossed deck, and the surveyor hauling a ton of brass up a mountain pass.